Okay, for part 2, what we're going to be looking at is torque and the center of mass and stability. So what is torque? Torque is a force that will cause things to rotate. Now, when you rotate something, you have to push through the off angle to the center of mass. So here's my phone. If I just push up at the center of it, it doesn't rotate. But if I push to the side, it's going to rotate, right? So to cause a rotation, you push off the axes, the center of it. And so anyway, that distance that you are from the center of rotation, that is called the lever arm distance. So here's your center of rotation. Okay. Or if you're doing some things, they might call it the fulcrum. But anyway, that's the point where you're rotating around. I also sometimes call it the hinge point, because like a door swings around on a hinge. Okay, so that's another way you can think about it. And to make a door open, you don't push on the hinge, right? Instead, you push on the handle, which is located far away from the hinge. And that's to give you the greatest lever arm distance. So you push with a force, okay? In this case, the force is the weight. And so this ruler will start to rotate. So force times distance. But in this case, that is not making work because these are perpendicular to each other. Okay, so these are 90 degrees to each other. And so one way to think about this is it's R perpendicular to F. Whereas we did work was force times distance. But remember, those had to be parallel to each other. Okay, so what this does is it doesn't add energy necessarily to the system. Now you can add kinetic energy with force, but anyway, yes, you are causing it to rotate. Now, so force and lever arm distance have to be perpendicular to each other. So in this first picture, you've got someone who is pulling on a wrench, but they're not pulling at 90 degrees. And so because of that, you can't count this whole distance as the lever arm distance. Instead, you have to figure out what component of it is perpendicular to the force. Okay, so you can only use the part that is perpendicular to the force. So it's better to put your hand so that you are perpendicular, and then you get to use the whole lever arm distance. If you want more torque, well, you can be like a plumber. Plumbers have those giant wrenches. And the thing is, what you're doing is making a longer lever arm distance. You can get those rusty nuts to rotate. So yes, try that. You can see that in this case, not having a big plumber's wrench, they just added a pipe and pulled harder. So yes, more leverage, more lever arm distance means greater torque. So here's one of the pictures of your book, and she's got the instructor has a croquet mallet, and there are places where she can hook on this weight. And so the kilogram weight here, putting it further and further out. Let's quickly figure out what force that is. And so let's say her distance is 30 centimeters here. And this is 1 kilogram of mass. So the force, don't forget, is the weight, mg. So that's going to be 1 kilogram times 10, or 10 newtons of force. So be careful also that you always make sure that you've got the proper units. Okay, so mass is not what you need weight. And also, of course, if we want to do this, torque is sometimes written kind of curvy looking. All right, so it's kind of written like that. All right, so torque, instead of just a straight T, it's more of a kind of a Greek T. So we're going to have our lever arm times our force, or you can do force times lever arm. In this class, it doesn't matter. And so 30 centimeters, I'm going to make that into 0.3 meters. And I'm going to multiply by the force, which is 10 newtons. And so that's going to come out to 3 Newton meters. And we just leave it as Newton meters because it doesn't make a new unit because they are not in the same direction. Okay, so it's not a joule. So torque is often measured in foot-pounds of torque here in the United States. So if you're tightening a wrench, if you have a wrench that has a readout, so that you don't tighten things too much. So when you're putting nuts on to a car, they have fancy wrenches now that give you the readout. And we'll do that lab in class actually too. Now, when things balance, it's because they have equal amounts of torque. So here we have our classic fulcrum. Okay, and we have a large seesaw here. And so when we're talking about equal torques, what you're talking about is the torque on the left side balancing the torque on the right side. Okay, so what we've got here is on the left side, we have a distance of 3 meters, and 250 newtons is the weight of the girl. On the right side, we've got 1.5 meters, and we've got 500 newtons. So, is the torque the same? Well, we've got 750 Newton meters on this side, and, yep, 750 Newton meters on the other side. Here's another example. We've got a woman who is weighing bananas using this sliding weight system. And so if you ever did a pan balance when you were younger or in chemistry class, you slide the weights along, right? That's the same thing. You're trying to balance what's in the pan with the weights on the lever arm. And so you're getting your pan balance to level. Well, she's just got a simple one here, and she slides the weight along until the bananas on one side balance the torque on the other side. And this right here is your rotation point, right? So let's do the math here. So the mass of the bananas is 1.5 kilograms. But 1.5 kilograms is going to be 15 newtons, right? So remember, we're going to use proper units here. We've got the distance, the lever arm distance to the banana is 5 centimeters. Now we can just leave that at 5 centimeters if we want. And then our answer will come out in 5 centimeters. Because we have the same units on both sides, okay, as long as we have the same units on both sides, then we're going to be okay for the missing units. Okay, so we know our units are going to come out in centimeters if we put centimeters in. The mass of the weight there is 0.25 kilograms, so that's going to be 2.5 newtons. And I could have just left that as kilograms, except we might as well make it into a force, because it's supposed to be force, not mass. So what is the distance of that, the missing distance on the right side? Okay, so I'm going to solve for R. 5 times 15 divided by 2.5. 2.5 will go into 5 2 times. So I would end up with 30 centimeters, right? Okay, so 30 centimeters should be how far out this is. So whereas if this is 5, then that's 5, 10, 15, 20, 25. Yep, around 30 centimeters. Okay, so anyway, so that's how you do torques. And balancing of objects. That's why things can stay upright. They have balanced torques. Okay, now another part of this is about the center of mass. And objects have a center of mass. And if it's a flat object, it's pretty easy to find. There are mathematical equations that help you to figure out where the center of mass is for various objects. And the center of mass usually is equal to the center of gravity too. So that's another way to call it. So center of mass is sometimes called Cm. Center of gravity is sometimes called Cg. And sometimes you can put dots if you want to. All right, there we go. Anyway, so the center of mass is the average position of the mass distribution. And the center of mass and the center of gravity will be the same if it's a uniform gravitational field. So usually close to the Earth's surface, we consider it fairly uniform. So you would have to have something very large or in some sort of weird gravitational field where you would not have the center of mass equal to the center of gravity. So the moon actually has that issue. Okay, so you can see how on a flat triangle, the center of gravity is 1/3 of the way up the medial line of the triangle. On the cone, the center of gravity is only 1/4 of the way up because you have so much weight on this side, okay? But there's some weight very far out on this side. So that's at a longer lever arm distance. So it's not, so you have to take into account the leverage. Things balance at these points. So objects will rotate around their center of mass when you throw them. And of course, the ball is easy to see, but here's a baseball bat, and you can see how the center of mass is not in the center of the length. It's a little further along. So what happens is the longer handle part is rotating around further out than the end of the bat that you hit with. Okay, so anyway, so yeah, so when it's circling around, it does look a little bit crazy. You've got this end going like this, and you've got this end circling like that. Sorry, did that wrong. It's like, why did I do that? Okay, all right, and you've got the other end circling like this. Okay, all right, and okay. Anyway, so anyway, here's a wrench, and you can see how the center of mass is that white dot. And this wrench was dropped straight downwards, but I had to turn it sideways to fit on the slide. But you can see how the center of mass is close to the head, the jaws, and it's circling around as it falls. Now, humans also have a center of mass. For most people, it's close to where their belly button is. And here you can see this guy is rotating around his center of mass, right? And so then as he starts to come out of the rotation, he extends his legs. And that's something that gymnasts and stuff have to do. We'll talk about that a little bit later. And here's a scientist swinging. And the idea is that his center of mass must be underneath where the rope is pointing here, okay? Okay, so if you try to balance a ruler, of course it will balance in the center of the ruler because it's pretty much equal mass all the way through. Equal mass, equal density distribution. And so you can hold it up at one point, and that point acts like all the mass, the entire weight of the stick is centered at that point. And so you can use that mathematically as the where the location of the weight is. And if you are trying to find the center of mass of a flat thing, well, then you just have to hold it up. And when you hold it up, what will happen is the point where you're holding it, the center of mass will swing down underneath that point. So as I hold this up, if I drew lines across my book, which I'm not going to do today, then what would happen is they would meet and cross in the center. So you can have any weird shaped object, and you can find the center of mass by holding it at different points. And so here's a map of the United States, and you can see that all these lines, you've held it at this point, and now at this point. And they all meet in one spot. Now, where's the center of the United States? That would be in Kansas. Okay, so anyway, Kansas is the geographical center of the United States if it was flat. This is the Fosbury flop. There was a guy named Fosbury who was an athlete. He wasn't the greatest athlete, but he started winning. And he started winning because he started doing things differently than anybody else. Everybody else in those days, when they go over a high jump, they would go more forward or sideways. So they would throw themselves over and then their legs, but they would do it sort of in a forward direction. Fosbury started doing it backwards. So he was going like this, and he would contort himself. He was this long, skinny dude, to this curved shape. And he started winning where he shouldn't really have been winning. Other people were much stronger than he was, and they should have been winning. Anyway, so physicists figured out what was going on. What was going on was that Fosbury was contorting his body so much that his center of mass was no longer on his body. It was down under his body. So his center of mass might be down here underneath him. And that's not that unusual. Think of a donut. A donut has a hole in it, right? Where's the center of mass? Well, it would be in the center of the donut, right? Or here's a boomerang or a banana. The center of mass can be off to the side. It doesn't have to be on the object. So when Fosbury was bending himself over like that, his center of mass was underneath. Well, what this meant was that when you use your muscles to give yourself a jump, the height that you jump to depends on the force you're able to exert and the force you're able to use to raise your center of mass a certain distance. And so what was happening was that Fosbury was only raising his center of mass a certain height. Let's say that this is 4'2" or something. Okay. All right. But because of that, he could go over a pole that was actually higher. Let's say it's 4'5". Okay, so he was actually able to get his body over the pole while his center of mass went under the pole. So his body went over, his center of mass went under. Anyway, so that means he didn't have to be as strong. He could get higher and get over that barrier. So anyway, then everybody started doing it, and then Fosbury wasn't really winning again. Okay. Another thing in this section is about stability. Objects stay balanced, okay, when their center of mass is over their base. So their center of mass, so here's this guy's center of mass. All right, and what he's got here, his torques are balanced. That's why that's his center of mass. The torque on the left side and the torque on the right side are in balance. And what he's able to do is by putting his arms here and by being a very skinny, strong dude here, he's able to put his center of mass over his base, which is his hands. So he's able to support himself on his hands. Okay, now, so the idea is to be stable, your center of gravity must be centered over the support structure. So here are some acrobats, and you can see the girl in the middle is on one hand, so her center of mass must be here. Now, how did she get it to go there? Well, she's got one leg way over here, she's got one arm way over here, and so those are pushing the center of mass over to the side, like Fosbury did. And so the other girls are still on two hands, but hopefully they'll let go soon. And so they are adjusting their legs. So this leg needs to go further over. and that will bring her center of mass probably where she needs it. Okay, so then her arm goes out like the other girl, and then she can stand on one hand. So the idea is you can adjust the center of your mass so that you can do weird balancing things like that. Okay, so here is this eagle. Maybe you've seen these before, but what this is this eagle is rotating around its center of mass. And its center of mass is not where you might expect, because looking at this eagle, you think, oh, well, the center of mass should be in the center of the body, right? But the thing is, what they've done is these wings are sweeping way out, and they're weighted usually on the ends of the wings. And so what that does is that brings the center of mass further forward till it's right where the beak is. And so the bird will now balance on its beak. Okay, so anyway, so that's moving the masses, so like Fosbury, until the center of mass is adjusted. The Leaning Tower of Pisa. Okay, well, things were getting a little iffy there. What was happening was the Leaning Tower was going so far over, tipping, that if you put a whole bunch of tourists up here in the top, then what they could do is add a lot of weight that would shift the center of mass over. And then what might happen is it would exceed the base. And so when the center of gravity exceeds the base, then what could happen is that it could fall down. And so they had to stop letting tourists in the Leaning Tower of Pisa, and then they pushed it back up a little bit, and they put lots of concrete around it. So now it's safe for tourists to go in there again. But yeah, you don't want your center of mass to exceed your base. And so if you've ever tried to bend over when you're close to a wall, then you know what can happen. When we bend over, we push our bottom end backwards so that our center stays over our base, okay? But when you're against a wall, you can't push your bottom back, and then what happens is your center exceeds your base, and you can fall down. So unless you've got really long clown-type feet, then you might be able to stay upright. And so you, of course, have probably, when you were a kid, you leaned backwards in your chair, right? Let me guess. Everybody does. So you're at the dinner table and you're bored, and you're like leaning back in your chair, and you're cool. You're definitely cool, right? So you're sitting there leaning back in your chair, and everything's fine until you lean so far back that your center of mass exceeds your base. So here your center of mass might still be, oh, barely within your base, which is going to be the chair in this case. But once you get over here, your center of mass is exceeding the base, and all of a sudden you start to fall backwards. So what do? Well, usually what you do is you throw your head forward, which has a lot of weight on it, has a lot of mass, and that pushes your center of mass forward till it's over the chair base again, and then you rock forward, and then you try to look cool, and your mom's like, see, I told you so. Anyway, so yeah, so you got to keep that center of mass over the base or you fall down. Okay, so some objects can tip further than others before they fall over. And usually that's because they have a wide base, like we talked about. Big feet would help that girl a few minutes ago. A wide base or a low center of mass, because that helps too. So race cars that have to go around corners are built low and wide, so that they don't tip over on the corners. Whereas race cars that just have to go straight, drag racers, they can be built long and thin, and nobody cares because they're not going to tip over. They're just going straight. Anyway, so here you can see how it has to do with angle. So this can has a center of mass here. And the idea is we can tip that can till the center of mass starts to exceed the base. So if it goes any further, it's going to be outside the base of the can. Inside the base of the can will just settle back down. So try tipping something right now. Maybe you've got a box in front of you, you know, or something. You can push and push until it tips, right? So there has to be a certain angle where it's going to exceed the base. So for this one, you can see how that looks like it's about 30 degrees that you're able to tip this can. But the next can has a much wider base, so the center of mass is at the same height, but the base is so much wider that you can see that the center of mass has to go much further. So this angle is looking like it's about 45 degrees. Now, the next piece has a very low center of gravity because it's very narrow up on top. It's pointed at the top. Most of the weight is down below, so the center of gravity is now lower. So it has the same diameter as the previous one, but the center of gravity is lower. And now as you try to tip it, you can see that the angle that it has to go through is a much larger angle. This angle is huge. So we're looking at 60, maybe 70 or more degrees there that this one has to tip before the center of gravity actually exceeds the base. Okay, so anyway, so wide base, low center of gravity, that helps objects remain stable. And so unstable things, you have to push them further and further and further. Okay, and that's the end of part 2. So let's stop this.